welcome to this lecture video all about resonance and damping. That's C4.3 on the IB spec. I'm generally following the structure of the Cognity textbook for this. You can recognize those outcomes on the screen. However, if you're studying any IB textbook, this should be helpful, or indeed any advanced physics course, this should be helpful on the topic of resonance and damping. Just a small point before we begin, please do feel free to hit pause whenever you need to. I think there's a lot of content in this. Really, I could have made 2 videos out of it. So take your time with it. I do encourage you to take notes, be active when you're watching. If you're any of my students, you should have some kind of structure strip which will help you work through the problems. So use that as a guide. I'm sure I can make them available to everyone. And finally, regardless of who you are, please do ask questions or give comments underneath the video. It does take quite a long time to make these videos, so any comments are really, really helpful, even if it's just to point out that I've got something wrong. So, assuming we're ready to go, let's get to it. We're going to begin with the idea of forced and free oscillations. Now, hopefully, you'll know what an oscillation is. We generally tend to think of oscillations as a sort of repeated process, for example, a vibration, which has a constant period t. Now, so far in the course, we have considered what are called free oscillations, and that's not necessarily a term which we've used necessarily in our lessons, but an example of a free oscillation would be the pendulum. Now, the pendulum oscillates freely. We give it initial disturbance. However, after that, it is free to keep going. And this could also be applied to, for example, our mass on a spring, more of which later. Now, the key thing about free oscillations is that they will oscillate at something called the natural frequency. And that's just the frequency at which the system will vibrate or oscillate after it's been initially disturbed. So if we take our grandfather clock and we disturb it, there's nothing else to change its frequency, and its frequency will be independent of that initial disturbance. So using our knowledge of SHM, actually we can calculate the frequency of oscillation of certain systems. And I've written down a couple here which you should recognize. These are the equations for the natural frequency of, on the left-hand side, a pendulum, and on the right-hand side, a mass on a spring. And all we've done there is taken our period calculations and found the inverse of those. These equations are not on the IB data booklet. You do not need to memorize them. However, they are ones which you could simply come remembering the relationship that the frequency is 1 divided by the period. So, a free oscillation is one which will follow its own natural frequency. It then begs the question, what is a forced oscillation? Well, an example of a forced oscillation, although it may not appear obvious on the screen so far, is an earthquake. When an earthquake happens, the buildings will vibrate, they will oscillate according to the frequency of the earthquake itself. And so therefore, there's a little bit less freedom. It is forced by the earthquake. It's forced by some kind of driver, which is the focus of what we're going to be doing today. So just to be clear, our forced oscillation is caused by an external force, and the frequency of that oscillation is determined by the driver. So in the case of the earthquake, the driver would be the earthquake itself. It would be the tremor coming from that earthquake as well. And so we're really interested in how these forced oscillations behave and how they compare with our free oscillations. So let's see an example of this. Hopefully this will work. This is a video within a video, so my apologies if it's a bit clunky. So let me just hit play. Here we've got a forced oscillation. It's quite clearly stated on the screen. We've got 3 springs and they're oscillating. Now notice here they've all got the same mass. However, they have got different spring constants. And hopefully you can see there's a very different response from all of these guys. I'm just going to pause it for a second just to highlight a few things. We've got 3 springs here. For this, we could then calculate their natural period and therefore their natural frequency. So our natural frequency of that left-hand blue mass is going to be 0.796 hertz. Our red one is 1.125 hertz. And our yellow one has got 1.592 hertz. Now, I've chosen these values specifically because if you look at our driving frequency here, my driving frequency is very similar to, almost identical to that of the yellow sphere. And hopefully you can see that that yellow sphere is bouncing up and down. It's got a really high amplitude of response. However, what I'm going to do now is bring that frequency down to the natural frequency of the red sphere. Now, hopefully what you'll notice is that the response of this red sphere is going to start increasing because we've hit its natural frequency. However, the one of the blue and the yellow is still going to remain small. Okay, and this is the effect that we're interested in, the fact that the response of a system depends on the frequency that we choose to oscillate it with. So initially we had a high response from the yellow sphere, and now we're getting a low response. Initially we had a low response from the red sphere, and we get high response. The blue sphere remained pretty uninteresting the whole time. This is an effect called resonance, and that's what we want to really dive into today. Okay, to give a bit more detail then, what we were looking at in that previous slide was the response versus the frequency. And here's how you would graph this. This is a characteristic kind of graph that you get. On the left hand, on the x-axis I should say, we have got frequency, and on the y-axis we've got amplitude of response. If we were to do this a bit more systematically and start with a low frequency and then gradually build up our frequency, we would notice that the amplitude of response, that is the amount at which the system vibrates, would increase as we approach a specific frequency. We then go past that frequency, it then decreases. Okay? And this is our effect of resonance. When we have a forced oscillation, the magnitude, the size, the amplitude of that response depends on the driving frequency. Now that is something quite new to us. Usually we know that frequency and amplitude are not related in any kind of wave. We can have any wave with any frequency, any amplitude, they are independent. However, for forced oscillations, they are not independent. The maximum response is the point at which we reach that natural frequency. So when we were driving the yellow sphere, the yellow mass, with its natural frequency, it was vibrating really strongly. However, when we went away from it, it started to vibrate a lot less. So our natural frequency is the driving frequency, which produces the maximum amplitude of response. Now, this is the effect called resonance, and when we've hit that natural frequency, we sometimes call it the resonant frequency. So don't be surprised if you see both of those terms. We've got natural frequency and resonant frequency, which are both important terms for us. Now, if you imagine this in a system, this may be something we might want. We might want to drive something so that it responds very to a great extent. But actually, resonance is not always a very helpful thing. A good example is the vibrations in a car as it drives. Cars have springs inside them, they have suspension, and we don't really want our car to be bouncing up and down. Now, thankfully, we can get rid of resonance. We can lose this resonant effect through a process called damping. Damping is something which can allow us to avoid resonance if we don't want to. Bear in mind, of course, resonance can be helpful if we want a large response, but generally we don't want resonance to happen. We don't want that large response because it sometimes can be quite destructive, as in the case of an earthquake. If the earthquake's frequency happens to be matched the natural frequency of the building, it will vibrate in a large way and break. So let's talk really quickly about damping. We don't need to know too much about damping for the IB course. Okay, quick look at the graph here. If we look at, we can see 4 profiles here. One of them is a bit lightly drawn here, so just point them out. We have dashed lines here. This is our undamped response. Okay, this is our normal wave response. We then have something called light damping in blue. We have heavy damping in yellow, and then we have critical damping in red. And we just want to talk about the difference between these things. Damping in general is, hopefully you can see, the reduction in amplitude. So when we have any kind of oscillation, we will get a reduction in the amplitude due to air resistance, due to friction, and that will take energy out of our system. That causes the amplitude to go down. And you can see why that might be helpful in the case of resonance. If we have high damping, that's going to take the energy out of our system. It's going to stop that large response and stop things, for example, breaking. The three different types, if we have, sorry, let's really quickly go through this. This is generally causes a loss of energy, a loss of mechanical energy, so a loss of our kinetic energy and potential energy to thermal. So there's a lot of heating effects to do with this. So let's go for it. We look at light damping. You'll notice that the light damping, compare it to the undamped case, you have a very similar kind of profile. We have a wave, and crucially a wave which has got the same frequency, same period as the undamped case. So that's an important point to make, that we have constant period. We just have a declining amplitude, and that will eventually hit zero after a few oscillations. We have heavy damping. Okay, heavy damping is a case where we essentially have no oscillation. Right? If you notice there, we are going from our maximum point straight down to zero. We never end up with any kind of full vibration in this case. If we have critical damping is when the system essentially goes right back down to zero. Okay, so we go straight to equilibrium. It's, if you like, the heaviest of the heavy damping. Okay, so these are our three types of damping. As I say, we don't really need to know too much about it. You need to know the idea that damping can take energy out of the system. The reason we started talking about damping, however, was to do with resonance, and this is key to us. I'm going to slip onto another slide to show you this. If we look at resonance versus damping, we saw in our previous slide that the amplitude of the forced oscillation is high when we have our resonance. And we've got, this is a system here, this top graph here is a system which has got light damping. Okay, you see here we've got a large response when we hit our natural frequency F0. Now, if we then move to a more heavily damped system, so if we add damping into our system, as we said in the previous slide, we lose energy. That mechanical energy becomes thermal energy, and the amplitude of our oscillations go down. So you can see here we have a more heavily damped system, and you'll notice our amplitude of response is much lower, actually much more consistent, much more kind of there's a smaller range between the maxima and the minima there. Now, crucially, you'll notice here that our amplitude of response actually hits its peak at a slightly different point. So when we have a damped system, it loses the value of its maxima, but also the position of that maximum also shifts, and it shifts always to the left. So the more damping we add, actually the further to the left that peak will occur. So there's two crucial points there. We reduce the amplitude. In general, everything loses its energy and therefore reduces amplitude. However, the position of that peak then becomes much lower. Now again, we've done a bit of a whistle-stop tour there. It is worth thinking about systems where we don't want resonance to occur. I used the example earlier of the earthquake. If the earthquake frequency hits the resonant frequency of a building, it will have a huge response. So what we do is we deliberately put damping into our system so as to firstly change that resonant frequency, but also to reduce the amplitude of response and therefore allow our systems not to vibrate too strongly and therefore break. Okay. As I say, that's a lot of information in one, so I do hope that if you've got the time, take time to sort of review, maybe re-watch, add to your notes, etc. Please do ask any questions. You should be able to understand a little bit more about resonance by now and understand really the difference between those light, heavy, and critical damping, and then how they relate to resonance. If you have any questions, please ask them under the video, and feel free to, as I say, watch again or point out any mistakes I've made. I'm sure I've made them, and I'll get back to them as soon as I can. All right, thanks very much for watching. Bye-bye.